Hi, so today we're going to be talking about pathfinding using Dijkstra's algorithm. So this is sort of lecture 5 if you're counting from the tutorials included. And we're going to talk more about graphs and graph representations and go through the algorithm for Dijkstra's, and I'm going to try and show you how it's working, right? Which is why I've also got drawing in case we need to do that. So I'll just make sure I've got the chats up because chats are quite useful to see what the chats are like, and I'll just make that small. Right. So yeah, it's just useful to have the lecture chat. If you're in lecture chat, I'll go there. Oh, the lecture slides on the wiki. I should have put them up already. Sorry, I forgot to do that. They'll be up after the lecture. And also the chat for Zoom. Make sure my chat is visible there. Right, okay, so I've got the two chats visible now. That's great. And we're recording. So, going to talk about about Dijkstra's algorithm. So we're going to talk pathfinding, graphs and search techniques for pathfinding, and specifically Dijkstra's algorithm. So pathfinding is used in a lot of places. You can do pathfinding in robotics. I remember back one of my honours students about 20 years ago did pathfinding as his honours project. Went on to do pathfinding as his PhD at Stanford, and his code ended up on the rovers on Mars. So, you know, pathfinding goes all the way from little robots like this, which is similar to what he did, all the way to actually having a robot on Mars. I also teach games, and so game pathfinding is quite a challenge. You would have noticed that in some games, the pathfinding fails. And one of the obvious signs that a character is an AI is when it does its pathfinding really badly and gets all confused. And, you know, we can also do pathfinding and planning in MetLink or in Google or Apple Maps. There are lots of tools for pathfinding. So it's a useful kind of common feature. So if we're going to look at pathfinding, what do we mean by this? Well, we mean that we're looking for moving a person or an entity through a group of nodes to a goal, right? So we're going from a start node to an end node. Now, if we had a look at the map, say from Kelvin Campus down to Courtney Place, then I've got to walk out from where I start to a node A. I can then either go down the Wiggly Street down onto Willow Street there, or walk along to the terrace and then go down Dixon Street, right? So I've got these two paths that I could do. So which one, if you were planning, is faster? Well, we build a representative node graph of this, and we say, well, there's start node, there's a cost to getting to A, there's a cost to getting to B, there's a cost to getting to C, a cost to get from D, from either B or D, and a cost to get to G. So this is, we've now represented the walking costs, say, of these. Now, these aren't necessarily topological, geographical representations. It's not saying, well, this is exactly this distance, so it will be that number. It's this is just a number that is the cost. It could be that, you know, if you have to go straight up a hill, I'm going to add more cost to that because that's hard work. And I certainly know that people down at Tiaro will look at Kelvin Campus and go, wow, that's a long way away. Right? Whereas if I'm up on Kelvin, getting to Tiaro, not so bad because it's downhill all the way, right? So I could change my costs according to how much effort it is to do this. So, pathfinding. Well, we want to go from a node, right, to another node, or we want to find out from this node what is the shortest path to every other possible node that I could get to, or I want to find all of the paths from all of the nodes and find all of the shortest networks, right? So you can do kind of a straight one-to-one, or you can do one-to-many, or you can do all-to-all. These are can be built one at a time, or they can be integrated together. So we have some ways of doing this, and if we're just looking for any connection at all, so we don't really care how, we're just seeing if two things are connected, then we can do something called breadth, where you can do either breadth first or depth first search. Breadth first search, and Dijkstra is a version of this. Breadth first search is where we search out broadly, and we always explore the thing that's closest to us, right? So we're just expanding out on across the breadth of the network. Depth first search is where we pick one and we go all the way down, and we just keep following until we get to either the goal we're talking to, or we get through the whole network. And we may search badly. Now, you did some of this in 103, so hopefully this is mostly reminder. And then there's random walks, and where you just kind of randomly pick and wander around and just seeing if you get anywhere interesting, as well as some versions of systematic expansion. So if we're going to talk about graph search, we then have some words, and we're going to talk about those words. So we refer to something as a fringe, right? Like your fringe here. The fringe is the edge of things, or the frontier, right? So, you know, Star Trek, A New Frontier. That's the front edge of your search. And when you're searching from your start node to your end node, then you're actually doing, you make your fringe around the start, and you expand the fringe out until you find the end node. It could be you search from each end. You could start from your end node and from your start node and start working towards each other, right? There's another kind of search, is where you do one step forward from the start and one step back from the end, and then you try and hopefully meet in the middle, which is quite useful if you know something about both ends. You might be able to make a faster search than if you just keep expanding until you just hope to hit the edge. But that's the fringe, the idea of the edge. So the data structure for the fringe, we could use stacks or queues or priority queues. The priority queue is the one we're going to talk about, because that's one that sorts the top of the queue for you. Whenever you put an item in, it will sort it to the top, which can be extremely useful. I'll just check everybody can hear me. We seem to be getting comments appropriately, so I'm pretty comfortable you're listening. And I will just make, yes, I am indeed recording with audio this time, because I remember one lecture I did without audio, and that was extremely annoying. So we start that fringe with our start node, and then we repeat until we meet our stopping criteria. We choose a node from the fringe, and we then visit that node, and expand it out, and we add all of its neighbors to the fringe and remove the node from the fringe and expand the leaf node and grow the search tree, right? So the idea is that we're doing this constant expansion of our nodes. So if we have an example of a depth first search through all nodes, so DFS, depth first search, so we use the stack as the fringe, right? So last in, first out, because for a depth first search, the idea is I'm just going to keep going down until I get to a leaf node, and then step back up and then go down again until I get to the end. So it's very simple. We start with an A at the start, at the top there, and then we go, okay, well, we visit A, and we add B and C to the fringe. Now, because we're starting, so we add B first, then we added C. We take C off because that's at that end of the search string, so that's there, and so we take it off, and now we visit A and C. And now we add any children of C. There were no children of C, so we look back at the fringe and go, oh, B's left in it, so let's take B out, put it down the front, so that B there moves down to the B, visit B. Then we have a D and an E, and we say, we look at that, and we say, well, now we've visited A, C, and B. Then we go, well, the last one on was E, so we visit that one, and then we visit D, and we've done, right? So we've now gone and visited every node in the graph, and we can say visited, and we could say the order in which it was stored. Now, we often talk about this as post-order and pre-order and in-order. If these was an ordered graph, we'd actually be able to, by the way that you return the depth first search, you can tell something about, not everything, but you can tell something about the shape of this graph by the order in which these numbers come back, right? There are some graphs it could be and some graphs it couldn't be, right? Because of the order in which these numbers come back. Does it always go right to left? It always goes right to left if you inserted nodes left to right. Because it's using a queue, it will take off the last one you added, and so if your last one you added was a right, it's going to take off the right. If you added them from right to left, it will take off the left, right? So that would be the difference. And I just need to click there, and then click here. So I need to get that so I can see it. That's good. So what is the data structure for the fringe of a depth first search? Well, you know, the simple one is just going to be, I kind of mentioned it up the top there. Which one? Is it for the depth first search, do you want a stack, a queue, or a priority queue? What are people's thoughts? Stack. That's some good work, Tarsi and Lisa. Yep, excellent. Stacks are all the way. Yep, that's how we go. That's how we roll. A stack, because you put it on, you pop it off. Easy JavaScript stack. You're just adding and you're building up a visitor list, and you have a fringe list. The fringe list has a stack. You pop it up, you push them on, pop them off. It just works. Okay. So Dijkstra's algorithm, instead of doing depth first, now tries to do a breadth first search, and it wants to find the path back, right? Because if you look at this path to D by going A, C, B, E, D is going A to C. How did I get to B? I had to go back up through A and then down to D, then out to and out. That would be a terrible path, and that's not a path at all. This is just the order in which they're visited. So that doesn't even give you a path between A and D. So, you know, it's the best you could do is potentially say, well, I'll store some parent information, and it would be harder. So how do we store that parent information of how did I get to where I am, and how do I know that the way I've got to where I am is the minimum it could be? Well, so we use a graph search technique, and again we start with the fringe being the start, and we always expand the unvisited node. So rather than the right to left, as was pointed out here, we now are going to be expanding the one that is closest to the start. Okay, so we systematically look at the distance we've traveled and always go with the closest one. It has to have a minimal cost from the start node, and we expand it and visit the fringe. And so when we expand, we visit, we remove it from the fringe, and we add its neighbours to the fringe. So again, we expand out. Now this requires, if we're going to actually find a path through it, right? For this purpose, we have a data structure, calling a search node. In my code, I've called it a path node, search node, path node, similar concepts, containing the node, the cost, and who was your previous. So where did you come from? Because we're going to use that to calculate the shortest path from the start node to the end node we hit. Okay, so remember cost, the node, and the previous node. So we're going to look at these costs and nodes, and try and work out what we've got in terms of moving through the graph. So as pseudocode goes, how the Dijkstra algorithm works is that your input is a weighted graph with a start node. The shortest paths from start to the output is the shortest path from start, and this algorithm is to all nodes. We could stop early if we actually had a to an end node, but I'll talk about that in a minute when I show you our code. But the idea is the first algorithm just goes me to everybody. So how does this work? Well, we start by setting my first node, the node I'm on, to being 0. the cost of being 0, and the first node is start, and I have no previous, right? I have a null previous pointer because, there isn't anyone before the start, and the cost of the start is 0. So while the fringe is not empty, and by adding the start node to the fringe first, it means the fringe has got one thing in it. So we know we're going to be able to proceed. We expand that cost. We expand the fringe node by taking a fringe, saying, right, okay, we take this one, which is the lowest cost element, and I'll show you the diagram of this. You take the thing with the lowest cost off the fringe. You say, right, if that has it been visited yet, right? So if the one on the thing is the lowest cost and it hasn't been visited, we're going to say, right, that node has now been visited. We are going to set its previous for the node I'm currently visiting to the node I was at, right? So the new nodes that I'm visiting, its previous is going to point back to where I just came from, and the edge is going. And so for each edge on this new node that I'm expanding, that are in the neighbor set, right? So each node in the neighbor set. So there are various ways you can find each edge in that in the outgoing neighbor, for example, which are outgoing neighbors of the node. If the neighbor is unvisited, right? So if I haven't already pulled it out of the network, then set the cost to being the cost that I have plus the cost to that node. Right? So for all node, and then you go through, add the new element to the fringe, right? So when you find that cost of the new node, you add it to the fringe. Okay, so there's a lot of concepts there. So this is reading through saying, okay, that's how I have to do this. So what does that look like in a diagram? And I've got two examples. So I've got this diagram, and I've got the diagram that we used from the previous assignment. I actually haven't drawn the numbers on, so maybe I'll do that before tomorrow, so you see the weight numbers. But those are the numbers from the Tute 1. But this is a different graph to Tute 1 graph. So we imagine we've got this A through H. Then I'm starting from G, and I'm going to find all of the neighbors. So I add G, I add 0 cost, I'm in G, no previous neighbors. Okay. That gets added. I say, I've now visited G. And by visiting G, what I've done is I've looked at, I then take that out and add all of the children. So I add the B, so I add B, J, H, K, and F, right? So so B, J, H, K, and F. I add all of those to my fringe, right? So these are all now in the fringe, all 5 of those. And I sort them by this number, this 10, 6, 8, 14, 25. They're sorted. Now, actually, if I'm using a priority queue, interestingly, it doesn't sort them all. It just sorts the top one. It says, just store them all there, but sort the top one, so I make sure that this is the smallest of all of them, right? So which makes it a bit easier than having to sort everything. So if we start here and say, well, okay, the 6 is the lowest one, right? You all agree the 6 is the lowest one? So we visit that and add additional nodes. Now, what have we added? So we've added A and C. And J is already on our list, right? But we now have a J coming from G, right? So J coming from G. And we have a J coming from B. So we could have gone up to B and then down to J, right? So I haven't visited J, so I'm still going to add it. So what is the next one we should expand? Type in a guess. C, we've got a C, a J, we've got a couple of J's there. We've got some voting on J's, that's great. Someone's going to vote on J down the bottom, possibly. So yes, the J is correct. We rather than C, which would be the 5 and would be 6 plus 5. We look in this thing and say, well, the 8 is the lowest cost, which is the G to J is the lowest cost. So that we're going to expand J with its previous node of G. So let's see that happens. There we go. 8 is the cost now, and we've gone from J, and we've got there by G, and so that's the one we're going to pick, and we pop it off, and that adds a whole bunch of more nodes. So we add all of its children, and we find out all their costs, and so we add all of these in, and now we have sorted. So as you see here, none of these are sorted, right? But so we need to sort this and find what's the lowest value here. What's the lowest value, and what are we going to visit now? H, J again. Ah, yeah, so we've got some questions here. If we look, the lowest one is this 9. And so that question of J again. Now, the reason we don't visit J, why wouldn't we visit J? What was in the algorithm before that said we wouldn't visit J? What changed about J? It's been visited. Yes, J has been visited. And so when we look at that 9 and go, okay, look at J, and it goes, oh, no, I've already visited J, I'll have to drop that one. The next lowest is H. Have we visited H? No. So we would drop that one. So that one, it's already been visited, don't need to do it. So we find the next lowest one, right, which happens to be the 10 there. So we go and visit H, and we add those to the fringe, right? So we've just whacked them on the bottom here. These last two are the children of H. Now we've actually only added the A and the K because we've already seen J, and so we're not G, so we're not going to add it now to the fringe. Right? So we've added an A and a K. We haven't visited any of these yet. So see, we've now got like 1, 2, 3 different paths to A. A would come through B, through J, or through H. So to work out the lowest of those, we have to have waited. That's why we have to add them in. We have to wait to visit A until we've got all the other short paths done. So H now, what would we settle on? What are we going to visit now? By my reckoning, I reckon we C, that one. Yep, that one. So we add that one in, and we go and visit it, and we can see we've added D and K over here down the bottom. So we've just added these two, and then we go, aha, this is the lowest one, and AJ. So we actually did do that eventually, that A route from J. So we visit that, and we get 12 AJ. And now, if we were to find the shortest path between G and A, how would we do that? Do you have anybody who's willing to say how they might find a path going back from A to try and find the goal G? Work backwards from A. Yep. And so what A has is A has a previous node. The previous node says, go to J. I go to J and then look at the previous node and it says, that's G. And I go, G, that was my start. So by storing these previous nodes, I can find the shortest path from G to H and to J and to B and to A and to C. And so I keep going and say, well, that's the next shortest one. So I visit that. And that one's already been, so you see this 13 here, when I go and visit it, it says, that A, I've already visited that A. There's no point in checking to see if the route BGA is shorter than GJA because I've already got higher than that number. So I cut that out. I check that one and go, oh no, I've already that one can be added, and it adds the link to F. I try that one, nope. I try that one, nope. I try that one, nope. Because I've now visited all of these, right? Which is why they're being cut out. So the next lowest is going to be this 14kj. I've already visited k, so it's going to be wiped out. The next is the 16, so E. Have I visited E? No. So E is the next one on my list. I go in there and go, right, E, you're added, and you add your connections to people who haven't been seen, and that's just F. So that's why you've got that last one, E goes to F. And now I've only got, I've got a couple more checks. That's 17. We'll see if, but C's already been visited, so that's going to be wiped out. And then I'm going to pick the F25 and go, well, actually that's visited, and I've now got every node done. So now we have mapped out basically the entire graph with previouses to say, well, if you want to get back to G, this is how you build that path from your end node back through those. And it shows you the minimum cost from G to every one of those nodes. Okay, and then, you know, that's Dijkstra's algorithm. Right? If you can kind of remember that, you're all good. Now, tomorrow we're going to go through. When I'm going to talk you through more of the code of how this works, and actually try and show you some more stuff around A star and stuff. So we'll get. What if you have a directional graph? Yeah, so if you have a directional graph, then as you expand, you can only look down edges that you have in the direction between you and your neighbor, right? So you don't use reciprocal edges. You just use the expanding edges, right? So we can. I actually have my graph here, which we can look at that. If you have directional graphs, what differences does that make, right? In terms of the paths it finds. It generally means that you might not be able to reach from one node back to another node because there isn't a path between these two. So this is for a bidirectional, every node is connected. When you have one directional graphs, sometimes you'll break your connectivity. So you only have one directional connectivity. It's different type. So that's a different. Directed graphs are different to undirected graphs. The moment we're looking at undirected graphs, it still works with directed graphs. Is this being recorded? Yes, I am recording it locally on my OBS. So I will upload that because I didn't steal host back from Dennis. Okay, so obtaining the shortest path. We can obtain the shortest path, as you correctly worked out, by obtaining the shortest path from the start node to any other previous node by stepping back through. So if we're going to go through from E back to G, we go E goes to D, bang, D goes to C, bang, C goes to B, bang, B goes to G. Right? So it goes bang, 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 and rebuilds that path. So this is what it might look like in pseudocode. So get the shortest path, you give a start node and end node, you have a path which you start with node and you have a current node, and then while the current node isn't the start node, you move the current node being the previous node, and you put that node onto the path, and then you return the path, right? So it actually builds the path up from E back to the start node, right? So once when you've reached the start node, you can end. If you haven't reached the start node, you keep finding those previous ones. All right, so if that makes sense, so E goes to D, goes to C, goes to B, and then down to E. Now, we could actually do a full mathematical proof, and certainly the math courses will do mathematical proofs of Dijkstra's algorithm. It was written at a time when mathematical proofs were the way that you convinced people of things, was by writing mathematical proofs, because computer programs were really slow and hard, computers were really slow, and so proving, like using lots of data and doing it that way, wasn't going to be convincing to anybody because you couldn't do enough of it. And so what we have here is that they use mathematical proofs. It's still great to use mathematical proofs to actually justify why you believe something to be true, right? Because just if you test it lots doesn't mean it's actually true. It just means you haven't found the counterexample yet. However, so the theorem of proof here is a programmer's version of a proof, rather than the mathematicians. So we actually, Xavier, one of our tutors, is doing maths. He can take you through the mathematical proof. I could do the mathematical proof, but most of you won't follow it. And it doesn't, yeah, and it's useful to do if you want to be able to prove things, but the concept here is that we are doing a lightweight kind of proof of concept rather than actual mathematical proof. So the idea here is that for each node is visited only once, because we check by that if statement. When it's removed from the so it's only visited once. When it's removed from the fringe, it then changes its state from unvisited to visited, and so it won't be removed a second time. If a future certain node contains the same node, it will be skipped. That's how we get rid of those. The minimum cost from the start node to a node is obtained when visiting that node, because we always search for the shortest path, right? So if we look at that, we're saying, well, Dijkstra's algorithm always expands the nodes that closest to the start. That's how we know that we're kind of always grabbing that the lowest cost node, and no shorter path from the start to the node after it's been visited, because we have that frontier has a cost, and we know that nothing on that frontier is going to get shorter. This, of course, relies on all weights being positive. If you happen to have a negative weight, that would be if you imagine that this graph was time and how long it took you to get from one point to another. If you had a time machine that if you took one particular path, you'd go back. If you went down at 88 miles an hour, you'd go back in time. Then your shortest path is kind of, well, I can't work out any shortest path, because just go down your time travel bit multiple times and that makes every path shorter. So there is no shortest path once you have negative time or negative distance, right? Then can't really work out paths. And so this all relies on these paths being positive, and adding together and not subtracting. Okay. Luckily, it's not a real world issue to have time travel. It makes things a lot easier. So the idea here is that we have a cost from the start to a node, and the cost 2 and 3, because of the way we expand, always going to be larger than cost 1 if we found cost 1 first. Right? So the data structure for the fringe. Now, in this, what we were doing here is we kept having to find on this list, we were finding the one with the lowest value, right? So this one here. Finding that is, you'd have to search through that entire list, finding, well, which of the fringe nodes has the lowest value. There are data structures that can help us with this. So we do that, we get to here. To understand which data structure we should use, we should need to understand which operations are most common, because you want a data structure that supports the most common operations. So the most common operations are going to be adding a node to the fringe, and then pulling the top node off, right? So the minimum cost node off. So we don't want to have to sort the entire thing. So there's two data structures. One is built into Java, and the other one you can build yourself. But they're both similar concepts. So we have a priority queue. Now, tomorrow's tute will go through how priority queue works. And we teach the cost of the priority. The priority queue says, put elements in me that have a certain priority. Tell me how many of the top you want me to sort. And I'll just store all the rest in whatever way they happen to be until you pop one off the top. When you pop one off the top, I'll then make sure I grab from my pool of other elements in my array the one that is the next lowest, right? So it has a structure that only partially sorts the array. So it doesn't go through and sort the entire array and then you just pull the top one off. Because if you're going to be inserting and removing and inserting and removing, you don't want to have to keep sorting every time, because sorting is costly. So you only really want to make sure, hey, if I'm adding one, is it lower than one down at the top? Well, yes, then make it the one at the top. If it's not, just throw it anywhere. I'll get to it later. Right? So it allows you to to add things to the queue without having to sort the entire queue. But always, when you pull off the top, you're going to get the highest priority or the best, the lowest number. And actually, so priority queue, you give it the number of ones that you want to be sorted. So I've got a couple of questions there. And it doesn't matter because it doesn't matter because we're only interacting with the top one, that we don't care about sorting the rest. So we can create an element for this with 3 fields in it: cost, node, and previous. Exactly. We create a new, like, we struct. Well, if we're in C, we'd create a we struct. We're in Java, so we create a we object. We create an object with these elements in it. I actually, in my code, I added a 4th element. Can you guess what the 4th element was that I added to this set of 3? Node, cost, previous. What do you think I'd add as a 4th element because it was useful? Any suggestions coming out there? No, it wasn't weight or total cost or previous cost or number of steps. No, it wasn't any of them. I have mentioned it. List of neighbors. No, it wasn't one of them. It wasn't the edge. No, you're hunting for it. Visited. Aha! Got there. Because visited was something I was using in here. I was using visited, right? Because I say, well, before when I'm doing here, I hit like that green, whether the node green or not, that's a visited structure. So I added a true false to say, have you been visited to this 3 struct? You could keep it as a separate thing. I added it to my struct for my path node. So I'd have the cost, the previous, the node I'm in, and a flag saying whether it's visited or not. So priority queue, so that's it's an array where the minimum one is stored in the top spot. The min heap is, you know how you've just done, well, if you've started looking at the tries, you build a tree structure with all the children, right? It's got like 50 children. A min heap is a tree structure where the only thing it cares about is the root node the lowest number, highest priority in the entire tree structure of heap of data. So when you add a new node at the start, all you do is say, are you smaller than the current root node? If you are, bang, you become the root node. Otherwise, I'll just put you down somewhere in the tree conveniently so later when I pop the root node off and I need to grab a child to make that the new lowest node, I know where to grab it from, and I grab and put it into the top node there. So the rest of the tree's not sorted, but every time I grab a node out to put at the top, I have a process by which it makes sure it grabs the smallest of the entire tree to put that there. Right? So there's a neat algorithm on min heap. Min heap isn't built in to the Java library, whereas priority queue is built in, so you can kind of save yourself time. Min heap is pretty if you like trees, but priority queue, because it's an array, actually beats the tree structures, because on disk arrays work better than trees, just from a pragmatic point of view. So priority queue is the one we're going to talk you through on the tubes tomorrow. So going through Dijkstra, if you have a one-to-one, if you know you're going from one direction to another node, if you want to, you can stop early, right? So if we want to find only one shortest path, we have a start node and a goal node, then we can stop faster. We don't have to search everything. And so we go through the weighted graph, and again, exactly the same code as before. We take the fringe, we expand the fringe, and we say whether it's been visited or not. And then we have this extra clause which says, oh, if you're the end node, drop out right now. Okay? So that's a kind of stop early mode. So in summary, if we're doing one-to-one, we can stop early. If your Dijkstra does all-to-one, well, one to all of them, you can do all-to-all, didn't mention it, but it's also solved by Dijkstra's algorithm. You can go through and find the shortest path from everyone to everyone. And if you have a directed graph, that's a very different number than if you have these undirected graphs, right? So in undirected graphs, your shortest distances are all the same. In the directed graph, in the directed graphs, your shortest distances will be different because sometimes you can take a wee short stop that you can't take in other places. And can we do better? Yes, we can. We can do better with A star because this is still a breadth first search. We just have a minimum cost. Now, what I wanted to show you, and this is a hint towards the code that we're going to have for tomorrow's tute, is if I go to my screen here, and you won't see me. So hopefully some of you will notice, will recognize this graph, and this was similar tutorial code. However, now I'm actually drawing paths between things. Now, how I'm drawing this path at the moment is I am just, this is now my current new start node. So when I click here, it's going to draw a path from this node to this node. So I can step around, and it's just going to draw paths to the next node, right? So every time I click, it kind of paths to the next one. What I'm showing you here is the result of the one-to-one Dijkstra's output on that graph that you have in tute 1. This will be the graph again we'll use in tute 2, and I'll start you playing with Dijkstra's algorithm, trying to get it to do this kind of thing, right? So the idea here is that you can see I've got the black nodes here are the visited nodes. The red are still in my fringe, right? I was looking at moving this into a compressed step, and it will step through and show you exactly the same sequence. This was easier to get going, so I decided to get going. And you can see here, when I click a root, you can see it going through my queue, which is the fringe, and setting of 9 to being a cost coming from 2. So you can see that I'm setting up these nodes, and these are the nodes in the path, and then I'm setting up these elements to have the node, the cost, where it's coming from, and whether it's been visited or not. Okay, so if I search a long distance, I go from there to here. It searched all of these nodes. It saw those but never visited them. Right? If I go from here to here, or back to this one, you can see it's going to step through these, and that one it had to visit every single node, right? Which is why this code says, go through all of the nodes, right? So it took quite a long time because it had to search the entire graph, right? So it was stepping through those entire graph, adding elements, and expanding the queue and popping those off. Now, so you're asking, should you implement this for the assignment? Not for assignment 1. We are now starting to talk about assignment 2, because assignment 2 has an A-star pathfinding requirement in it. It is going to be built on top of the current assignment you're working on. So the bus routes, you're going to use those again, but you're going to do pathfinding in those. Right? So we're going to start with Dijkstra's, we're then going to move on to A-star, and that's what you're going to do in assignment 2, but that's a few weeks away. So yes, it is useful to understand how this all works, because you're going to implement some of it. Assignment 1 is due in just under 2 weeks, right? So there are some, I know some students have actually finished assignment 1, so there are at least some people who have done all of that's required. But again, we haven't even finished all the first tutorials yet. So the tutorials help with giving you more code towards the assignment. So don't feel you have to have done the assignment by this point. I'm just foreshadowing what you will be thinking about doing when we move into assignment 2. And if you're really fast, you could then start working at that in the future. So should you start building a code for assignment 2 on assignment 1? You can, but make sure you've submitted assignment 1 as a working assignment rather than trying to do assignment 2 before you know what assignment 2 is. Right? But knowing that you might have to do pathfinding could help you decide with some of your data structures. Okay. I'll be giving the lecture tomorrow will be me talking more about this and showing you more of how this code works. Hopefully, does it make sense what I'm showing you here? That we have a node, it's got a number visited. I need to add the numbers on these weights. Oh, and by the way, I made the weight of the edges here 10 minus their weight. So short edges are black and long, like the long heavyweight edges are actually lighter colored because it's a more tenuous connection, whereas short nodes have a strong connection, and so I made these the thickest. Right? Okay. Do we have any questions? So what I thought I might show you also is so this is my solution code with the Dijkstra's algorithm in it. And we're not necessarily going to give it out because otherwise I'll steal your joy of coding. But what I will show you is the path node. So if I bring that down, so the path node I'm using, as you see, is a node ID, a cost, and a previous, which is what you might expect. Plus that visited is true, and standard a path node has these 4 things in it. You have get ID, get cost, get path. I have a toString, which is what you're seeing being drawn onto the graph. And down here, I have a reset my path. Every time I do a new search, I have to reset all those nodes. So I set them back to kind of unvisited. The previous is -1, which in my error case, and the cost is max double. So it's kind of as close to infinite as we can get. Is there a practical difference between priority queue and min heap? In a sense, yes. One is built on a tree structures, one's built on an array structure. Array structures tend to be faster, and so we use those. So when I'm going to use my priority queue, and I have a priority queue in my Dijkstra's algorithm, so there is a bunch of code there. But when I create my priority queue, this bit is interesting, which is when I'm going to search a priority queue, and this is what we'll talk more about tomorrow, and I'll go into because we're right at the end of time, is this idea of there being a cost comparator in there. And so this cost comparator is what we're needing to be for comparing path nodes so we can find the shortest one. But it looks like I have to cut that out because I just scrolled through my Dijkstra's algorithm, and some people will freeze screen the video recording and then try and see everything I've coded. So yeah, do actually try and do this code yourself. So that's what we'll be talking about tomorrow and the next day. All right, tomorrow and then the tutorials next week will help move you forward through the Tut 1 code and into this kind of graph searching Tut 2 code. Any questions? So if you make a heap in 103 using an array, that basically becomes that makes the priority queue and the priority and the min heap almost identical at that point. So practically they become the same thing. Okay, 6 o'clock. Have a great evening. I will go and work out what my daughter wanted when she tried to come into the room. Yeah, I'll put those slides up now, and I will remux this recording and cut the end off so you don't see all of that code, which I shouldn't have scrolled through. I should have just stepped out of and stepped back into. And we'll see you tomorrow. And I'll jump over to Discord while I do that, so if you've got any further follow-up questions, see you in Discord. And hi Twitch. I'm glad there was somebody on Twitch. Yay Twitch. Okay. So stop streaming.